Okay, good morning. Okay, let's start the class. So I believe today we will finish the discussion on combinatorics, and then we can move on to a new topic called sets. So far we have discussed these different cases. So we have talked about what is combinations and what is permutations. And then we have also talked about how to count them. So how many ways are there to choose R objects from n types of objects. So at the beginning, we have talked about the case where there are no repetitions. So each type you can choose either 1 or 0. So you have n types of objects, and then altogether you want to choose R objects. Each type you can just choose one time. So how many ways are there? So there's n choose R ways. Is that okay? So we define this term to represent the number of ways of choosing R objects in total and from n different types. Is that okay? So there are n people. I want to choose R people. We have also talked about the number of ways to choose R objects from n objects or from n types of objects at most once. And then the arrangement matters. So in this case, the number of ways is P n R. And we have also talked about the case where there are repetitions, right? So we can have apples, we can have oranges, we can have bananas. There are n types. And then we want to have a combination of R objects. How many ways are there? So in that case, you can think about it as there are R stars and then n minus 1 bars. And then from R plus n minus 1, a bit string of this R plus n minus 1, you want to find out which positions are to place the objects. So there are R plus n minus 1 choose R ways. Okay? So all of them are actually very similar to n to the power R. This is like n times n minus 1 times n minus 2. There are R terms altogether divided by R factorial. So this is like this one, n to the power R. But it is not exactly n to the power R, but n minus 1, n minus 2. So this is a falling function. And then divided by R factorial. So here, this is related to n to the power R, right? And this one is what? This one is Pnr. How many ways are there? So how many ways are there? So this is simple. So this is n to the power R falling. Am I correct? There are n ways to choose the first object, n minus 1 way to choose the second object, n minus 2 ways to choose the third object, and so on and so forth. So there are these number of ways. And what is it? This is similar. This is equal to n plus R minus 1, this number to the power R, but falling, divided by R factorial. And if you can switch your mind, so instead of looking at this one as n plus R minus 1 falling, it is actually n rising. So this is n to the power R rising divided by R factorial. Is that okay? N to the power R rising means that it is n and then n plus 1 and then n plus 2, n plus 3, and so on and so forth. They are altogether R terms. Is that okay? So if you look at it, the last term will be n plus R minus 1 because they are R terms starting from n minus 1. Is that okay? So it also looks like n to the power R. And finally, this is the case that we have missed. Okay. So we want to count. Okay, so how many ways are there? So there are n types of objects. So n types of objects, you can imagine one type is apple, one type is starfruit, one type is orange. Let's say what? One type is banana. Okay, banana. Oh, so this is banana. Oh, so let's say there are 4 types of objects, and then we want to have R objects selected. So we have R objects selected, 1, 2, 3. Let's say R is equal to 5. R is equal to 5. But the arrangement matters. So the ordering of this object matters. And then for each position, you can choose either of these things without restriction. So you can have all of them apples. So apples are unlimited. You can repeat apples. You can have stars repeated. You can have orange repeated. Or you can have bananas repeated. So there is a way of doing this, like you may have all of them are apples. Is that okay? So this is one way. Or you may have all of them. You may have this one apple, this one apple, this one star, this one orange, and this one apple. This is also another way. The arrangement matters. So in this case, how many ways are there? So there are n types of object, n is equal to 4. Here, r is the length. You are going to choose r objects altogether. So how many ways are there? How many ways? 4 to the power 5. Very good. 4 to the power 5. This is rule of product. So there are 4 choices in the first position, 4 choices in the next position, 4 choices in the third position, and so on and so forth. 4 to the power 5. And actually, in general, this is the term n to the power r. So this is the easiest case. Okay, n to the power r. We have been using this all the time. Okay, so let's take a look of a very simple example of using this. So let us look at the numbers. Let's look at all the numbers between 0 and 10 to the power 10 minus 1. Okay? Is that okay? So 10 to the power 10 minus 1 is equal to what? It is equal to, all of them are 9s, right? So it's equal to 9, 9, 9, 9, 9. Is that okay? How many 9s are there? How many 9s are there? 10. 10 or 9? 10. Very good. So there are 10 9s. 10 9s. Is that okay? So they're altogether 10 9s. Is that okay? 10 to the power 1 minus 1, there are 1 9s. 10 to the power 2 minus 1, there are 2 9s. 10 to the power 10 minus 1, there are 10 9s. Okay, so we consider the numbers. So here, the first question is, how many of them do not contain the digit 1? How many of them? And then the other is, how many of them do contain? Is that okay? Okay. So the first question is, so there are many numbers here, and then we want to find out how many of them doesn't have any 1s inside. So 0 does not have a 1. 2, 3, 4, 5, 6, 7 up to 9, it doesn't have a 1. But then 10, it has a 1. 11, there are 2 1s actually. 12, there is a 1 inside, and so on and so forth, right? So how many of them does not have a 1 inside? So this, yeah, how many of them? Let me give you a hint, okay? So you can think of each number here as a 9-digit number. Every number is a 9-digit number. So for instance, you have a number 23. So how do you think of it as a 9-digit number? You add zeros, enough zeros at the beginning. So 0, 0, 0, 0, 0, 0, 0. Is that okay? So this represents 23. Is that okay? Okay, so you add zeros at the beginning so that it becomes a 9-digit number. Okay, so every number here becomes a 9-digit number, and there is no repetition. Is that okay? So 0 will be all zeros. There are 9 zeros. 1 will be 8 0 followed by 1, and so on and so forth. Okay, does that help you? Okay, so if this number does not contain, so if this original number 23, let's say, it does not contain a 1, then this number also does not contain a 1. If this number, let's say 120, contains a 1, then the representation will also contain a 1. Is that okay? So you have 0, 0, 0, 0, 0, 0, 1 to 0. Is that okay? So that means that we just need to consider all the 9-digit number. How many of them does not contain 1? So how many of them? How many? Oh, very good. So I heard an answer. So the answer says 9 to the power 10. Why? Why is it 9 to the power 10? Why? The reason is that you can think of this as the selection problem. So you have 9 digits to choose. If you don't want any one, so there are 9 choices in the first location, there are 9 choices in the second location, and so on and so forth. So there are going to be 9 to the power 10 ways of choosing a number that does not contain a 1. Okay? Okay, good, excellent. And how about this? How many of them contains a 1? How many? How many? So how many? How many contains a 1? So the complement. Okay, so here we have altogether how many numbers? Altogether 10 to the power 10 numbers, right? And then 9 to the power 10 does not contain a 1. So how many contains a 1? 10 to the power 10 minus 9 to the power 10. So this is the answer. Is that okay? Is that okay? Now let me change the, is that okay? Now let me change the problem a little bit. So this is not exactly the problem in the lecture notes. So in the lecture notes, instead of having 0 and 10 to the power minus 1, we have a 1 here. We have 10 to the power 10 here. So what would be the change to our answer? So we, instead of counting from 0 up to 9, we count from 1 up to 1 and then 0, 0, 0. What would be the change? Would there be any change here? How many numbers do not contain a 1? So we are still counting 10 to the power 10 numbers, right? Yeah, we're still counting the same number of numbers, okay? But we shifted 1 position. Okay, how many does not contain a 1? So are there any change here? Yes, there is change here. Are there more numbers does not contain a 1, or there are fewer numbers does not contain a 1? Fewer. So the change will be minus 1. Very good. So this is a tricky thing. And if there is minus 1 here, then there will be a plus 1 here. Is that okay? Because the total is still 10 to the power 10. Okay? So this is the answer of the lecture notes here. Okay, but you notice that, okay, you should notice that the way to do this counting is still the same. Consider each number as a 9-digit number. Okay, so you may first ignore this first number here. You may start counting from 1 up to 9 here and make some modifications, make some adjustments. Okay, is that okay? Good, that's it. Okay, so we have completed the description here, but there are actually more. So, but this will not be the topic for the first year discrete math. So in total, so you can see that there are 1, 2, 3, 4, there are only 4 different cases here, right? But there can be altogether 12 different cases. So we are talking about only 4 different cases. Okay, so imagine, we have not talked about this one. So imagine you are having 3 dice. Each dice is 1, 2, 3, 4, 5, 6. Is that okay? How many ways to get 18? There's one way, right? 666. How many ways to get 17? Now to get 17, you can have the first one 5 and then the next two 6. Is that okay? Or 656 or 665, right? So using our method, we are going to talk about this as what? As the let me see. We will talk. Let me see. Is it the same as what we have been talking about? Let me see. So we need, there are 3 cases here, but if all the dice are the same, you cannot differentiate them. There is still 1 case. Is that okay? Do you understand my point? Okay, so we assume that if you can differentiate the 3 dice that you are rolling, then there are going to be 3 ways. Because either you have the first dice 5 and the other 2 6, or the second dice 5 and the other 2 6, or the third dice 5, the other 2 6. Okay? So this is the case where the dice are distinguishable. But we can also have a case of counting that the dice are indistinguishable. And in that case, we should be using a different counting method. Is that okay? Okay? So So this is a case that is not here, not included here. Okay, not included here. How many ways to get, right? How many ways to get 17? Using 3 dice, but they look the same. Okay, and then you should still have only one way. Okay, so for that one, if you are interested, you can check out from the internet about counting. Okay, so there are 12 different types of counting, and we have talked only about 4 of them. Okay, good. And now, to end the discussion of all the combinatorics, there's one big topic called combinatorial arguments. Or sometimes people call it double counting. And this is a technique to prove some identities that involves combination terms. So for instance, there is a, so last time we have talked about the Pascal triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So each of these terms are combination terms, and then each of these terms is the sum of the 2 terms above. So in general, we are saying that n choose R is equal to that term plus that term. Okay, so this is equal to n minus 1. So this is about the previous row. Choose R minus 1 plus n minus 1 choose R. We are claiming a result like this. Okay, so this is stands for n choose R, CNR. CNR is equal to Cn minus 1 R minus 1 plus Cn minus 1 R. Okay, how? How do we prove this? So one way is, of course, we can go back to the formula about this n choose R. So this is n falling, n to the power R falling divided by R factorial. And then you do some algebra, you find out these two are the same. Is that okay? But there is a better way. We create a story. So this is what we are going to do. We create a story. And then the story will help us to do the counting in 2 different ways. Okay. So that's why we call it a double counting. Let me show you a story here. So first of all, what is n choose R? N choose R. N choose R means that I have n objects, and then I want to choose R of them, and then how many ways are there? Okay, so altogether there are n objects. They are distinct, they don't look the same, and then I want to pick R of them, select R. R of them. Is that okay? Now, suppose that the first one is something special. There is a strawberry on it, and then you like it a lot. Okay? So to do the counting, for you, there are 2 different cases. One is the R objects will include this strawberry thing, and the other way is the selection of R objects does not include the strawberry ball. Is that okay? So there are 2 different ways. 2 different ways. One is this include this special one, and the other is it does not include this special ball. Is that okay? Now the total number of ways to select R objects must be equal to the number of ways to select R objects including this one plus the number of ways of selecting R objects but without this one. Is that okay? This is a rule of sum. There are 2 cases. These 2 cases are disjoint. Okay? So how many ways are there? So I want to select R objects, and it has to include this one. So how many ways are there? Altogether n objects. Altogether n objects. I want to select R objects from them, but then it has to include this one inside. So how many ways are there? How many ways are there? So this has to be included, right? So what I need is only R minus 1 objects from how many objects? N minus 1. So here, the number of ways here will be n minus 1 objects. I'm going to select R minus 1 objects. Is that okay? So this is the number of ways for this part. Is that okay? How about this one? This one, how many ways are there? So I cannot include this object. I cannot include the strawberry ball. And so I will need to select how many objects from the remaining objects? R. Very good, because I need to have R objects in total, right? And then where does these R objects come from? So they come from the remaining n minus 1 objects. Is that okay? So the number of ways to do the selection of the first type, which include this strawberry ball, is n minus 1 choose R minus 1. And on the other hand, the number of ways that does not include this special one is n minus 1 choose R. Is that okay? Okay? Okay, so the normal counting, the normal way, the first type of counting is just think about selecting n balls, selecting R balls from n balls. So n choose R. But then, in your story, you can create a special item here. Okay? So that after creating a special item, you have a different way of counting the number of ways to choose R items. And this is it. So this is this one and this one. You add up together, this is the number of ways. So we get this identity. Is that okay? Okay, so we will have more examples today. And then you will find that usually with combinatorial arguments, it is clear. You can explain this idea, why this is true, easily to your friend without using this algebra thing. So this is very, very useful, okay? And then I hope that you can learn this skill. So in the assignment, you will have a lot of exercise of this one, this type. Okay, so let us look at another identity. Okay, this is the identity called binomial theorem. So it says x plus y to the power n, okay, is equal to what? Is equal to n choose 0 times x to the power n plus n choose 1 times x to the power n minus 1 y plus n choose 2 times x to the power n minus 2 y square plus dot 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 up to the last term will be n choose n times y to the power n. Is that okay? So this is the so-called binomial theorem. So if you want to write it down in a more compact way, so this is the summation of all the possible R that ranges from 0 up to n choose R, x to the power n minus r, y to the power r. Is that okay? Okay? And then why is it true? Or how do we, so how do we prove that this is true? How do we prove that this is true? Now to prove that this is true, you can use differentiation, okay, with respect to x, or you can use differentiation, or you can use induction. Okay, you can use induction to help you. But the best way is like this. The left-hand side is about x plus y to the power n, right? So you write down the equivalent form in an expanded way. So you write down x plus y, x plus y, x plus y. You write down all together n times. So there are n times. Now the expansion of this will help us to find out why this is true, why these terms are true. Okay? Okay, so first of all, to get x to the power n, what do we need? How does x to the power n coming from? So x to the power n must be, I'm selecting this x, it is going to multiply with this x, and then it is going to multiply with this x, and so on and so forth up to the last x. This is the only way to get x to the power n as the coefficient, right? As the term. Okay, this is the only way. So there is just one way okay, to get x to the power n. Now, how do we get x to the power n minus 1 times y? We may be doing, we select the y here and all the x in the end, or we may select this y with all the terms, each one of them an x, and so on and so forth. Do you understand what I'm talking about? So to get x to the power n minus 1 times y, one way is I select this y, multiply with this x, multiply with the next x, and so on and so forth. So this is one way to get x to the power n minus 1 times y. This is one way. And then the other way is this time I may fix this y, I multiply with this x, I multiply with this x, I multiply with x, and then I multiply with all the terms x there. Is that okay? So this is another way to get x to the power n minus 1 y. And then how many ways are there? So you can fix y here, you can fix y here, you can fix y here, and so on and so forth. So there are altogether n different ways. Is that okay? Okay? Actually, how does this n come from? N is coming from, there are n different cases that you can choose y, and you need to choose one y. You choose which term you want it to be a y. So there are n choose one ways of selecting one y. Is that okay? And similarly, to get the term x to the power n minus 2 times y squared, among all these n terms, you want to find out which 2 you should be setting it to y, so that the remaining will be x. So there are n choose 2 times x to the power n minus 2 times y squared. Is that okay? Is that okay? That's it. That's it. So this is the way. So this is the way that we can show that this binomial theorem is correct. Okay, we are using arguments, the number of ways to get this term, as a counting problem. So we count the number of ways, and then it relates to counting how many terms that we need to choose it to be y. Is that okay? Okay. Good.